History's greatest collapses left their most honest records in the dust, while empires built monuments to their own glory. The truth of their downfall was written in a language we are only now learning to read. This is an investigation into the silent witnesses of our past. We will see how scientists use three subtle clues, hidden in pollen, volcanic ash, and ancient ice, to reconstruct the final days of vanished civilizations. By the end, you will understand how to read the landscape itself as a history book, one that tells a story often missed by kings and chroniclers. These clues reveal why mighty societies like the Maya faltered, and what the very air during the Roman Empire can tell us about its economy. They force us to ask a deeper question about the bond between a civilization and its environment. What story is our own world writing down for the future? To find the evidence for these silent histories is not found on parchment or stone. It is locked within three remarkable natural archives, each one a meticulous, unintentional recorder of its time. The first is pollen, a substance so common we hardly notice it. Every plant species produces a unique pollen grain, a microscopic fingerprint with an incredibly tough shell. When these grains fall, they settle into lake beds, bogs, and soil, building up in layers over centuries. By extracting cores from these sediments and identifying the pollen trapped inside, scientists can read the changing story of a landscape. A sudden spike in maize pollen tells of intensive Mayan farming. A decline in tree pollen followed by an increase in hardy weeds speaks of deforestation and soil exhaustion. Pollen is the enduring diary of what grew where, and by extension, what people were growing and how they were changing their world. The second archive provides the essential element of time, volcanic ash, known to geologists as Tephra. A major volcanic eruption is a global event, catapulting billions of tons of finely ground rock and glass into the stratosphere. This unique chemical and mineral signature then rains down across continents, forming a thin, instant layer in every sediment record, from the lakes of Europe to the ice of Greenland. This layer is a gift to detectives of the deep past. It is a perfect, simultaneous timestamp. If you find the same ash layer in an Italian peat bog and in a core from a Scandinavian fjord, you know those two moments in the sediment record happened at the exact same geological instant. Tephra turns a messy, relative timeline into a precise, connected calendar, allowing researchers to synchronize the collapse of a society in one place with a climate shift recorded thousands of miles away. The final and perhaps most comprehensive archive is ice. In the eternal cold of polar ice sheets and high mountain glaciers, snow falls year after year, each layer compressed by the weight of the next. These layers, like tree rings, form an annual record, but they capture more than just precipitation. They trap tiny bubbles of ancient air, dust from distant deserts, sea salt, and chemical compounds from human activity. Drilling down with a hollow core barrel extracts a vertical timeline of the atmosphere itself. A rise in lead particles in ice from Greenland during the height of the Roman Empire points to vast silver mining and smelting operations. A layer of sulfuric acid signals a massive, climate-altering volcanic eruption. Ice is the planet's own atmospheric ledger, a direct chemical sample of what the sky contained in any given year. Together, these three archives, pollen, ash, and ice, form a triangulation system. They are the physical, unedited data that allows us to move beyond what history says happened and begin to understand what the world itself witnessed. To read this hidden history requires a unique blend of scientific detective work. The first discipline is palynology, the study of pollen and spores. Researchers travel to ancient lake beds or peat bogs, places where sediment has accumulated undisturbed for millennia. Using a hollow drill, they extract a core, a vertical cylinder of mud that can be many meters long. Back in the lab, they dissolve the sediment with chemicals, leaving behind the nearly indestructible pollen grains. Under a powerful microscope, they identify and count thousands of these microscopic fossils, charting the rise and fall of plant species across centuries. The second key field is tephrochronology, which uses layers of volcanic ash as time markers. When that unique chemical fingerprint from a known eruption is found in a sediment core, it pins that exact moment in time to that layer, creating a fixed point on the timeline. The third discipline is ice core climatology. Teams drill deep into glaciers or ice sheets in Greenland and Antarctica, retrieving cylinders of ice that contain annual layers going back hundreds of thousands of years. They analyze the chemistry of the ice and the tiny bubbles of ancient air trapped within, measuring everything from greenhouse gas concentrations to traces of industrial pollution. To weave these separate threads into a single story, scientists rely on calibration with radiocarbon dating. Organic material like a leaf preserved in a peat layer can be dated, providing another anchor point. By combining these methods, researchers can construct a robust, multi-proven timeline. This is not archaeology in the traditional sense. It is forensic science applied to the entire planet, treating a lake bed as a crime scene and pollen grains as silent witnesses. This creates a profound shift in how we understand the past. For centuries, history was a narrative written by the victors, recorded by scribes in royal courts, or carved into monuments by those with the power to do so. These sources are invaluable, but they tell a top-down story of kings, battles, and treaties. They rarely mention the farmer whose crops failed, the price of bread in a distant province, or the slow creep of soil erosion across a hillside. This is where our silent witnesses rewrite the story. Pollen, ash, and ice are democratic historians. They record without agenda, preserving the reality of the everyday world. They tell us not what a ruler wanted remembered, but what actually happened to the land and air that sustained everyone, from the emperor to the laborer. The true strength of an empire was not just in its legions, but in the stability of its harvests. A core of sediment from a lake near a Mayan city does not contain glyphs boasting of a king's divine right. Instead, it shows a relentless increase in maize pollen, evidence of intensive farming to feed a booming population, followed by a telltale rise in pollen from tough, weedy plants that thrive in poor, eroded soil. The archive tells a story of agricultural strain, of a foundation being pushed to its limit. Similarly, the lead pollution frozen in Greenland's ice is not a Roman senator's report on economic output. It is the physical residue of countless furnaces burning day and night to mint coins and craft luxury goods, a direct chemical signal of industrial activity and trade that reached across continents. This environmental record provides a continuous, unbroken timeline where written history has gaps or silences. It offers a bottom-up view of civilization, measured in the health of the land, the consistency of the seasons, and the silent testimony of the very elements people lived with every day. It asks us to consider empires not just as political entities, but as ecological ones deeply entangled with and dependent upon their environment. When we learn to read this language, we begin to hear the stories of those who never wrote a single word. Among the great enigmas of the ancient world, the silence of the Maya cities stands apart. Around the 9th and 10th centuries, the bustling urban centers of the southern lowlands, places like Tikal and Kapon, were gradually abandoned. The grand plazas fell quiet, the towering temples were reclaimed by the forest, and a centuries-long flourishing of art, astronomy, and architecture seemed to simply stop. For a long time, this was a story told by empty stone. The monuments themselves offered clues: a last-dated inscription, a halted construction project, but they held no explanation for why a society of such sophistication would walk away from its own heartland. This is where the silent witnesses begin to speak, offering a testimony from the ground up. To understand what happened, we must ask what the Maya landscape experienced. What does the pollen trapped in the mud of nearby lakes tell us about the world they built and the environmental pressures they ultimately encountered? The answer transforms the mystery from a sudden event into a slow-moving story written in soil and spores. The story of Maya prosperity is written in the mud beneath their lakes. Deep within sediment cores pulled from the Patane region, palynologists find a dramatic, centuries-long signature. At the base of these cores, the pollen tells of a dense, diverse rainforest. Then, as Maya civilization expands, that pollen record shifts dramatically. The spores from towering canopy trees like mahogany and cedar begin to disappear. In their place comes a relentless wave of maize pollen. This is not a gentle increase, it is a takeover. The landscape was being systematically remade, with vast tracts of jungle cleared to create fields for corn, the foundational crop of Maya life. This pollen map reveals an agricultural empire, feeding cities of tens of thousands through an ever-expanding patchwork of farmlands. But the Maya were not just clearing land, they were engineering it. In the same sediment layers, scientists find another type of evidence, not from plants, but from the very shape of the earth. By analyzing the mineral composition and grain size in the mud, they can detect the fingerprints of human construction. These layers show the outlines of sophisticated canal systems, intricate networks of terraces carved into hillsides, and carefully managed wetland gardens. The Maya were master hydrologists, redirecting water with a precision that turned seasonal swamps into productive fields and captured precious rainfall. The pollen and the soil together paint a portrait of a society at its peak, one that had achieved an astonishing degree of control over its environment. This was a civilization that had successfully bent the forest to its will, creating a flourishing, engineered landscape to support its grand cities. For centuries, this system worked, a testament to human ingenuity. Yet this very success contained the seeds of a vulnerability, one that the silent witnesses would later record with chilling clarity. Yet this engineered landscape had a hidden fragility, one that depended on a delicate balance of rain. The pollen record tells us what they grew, but to understand why it all began to falter, we must look deeper into the mud itself, at the chemical and physical traces of the water that once fell from the sky. Within those same lake cores that hold the pollen, scientists find another set of clues written in the very minerals and fossils. During wet periods, the lakes were full, and fine organic mud settled calmly to the bottom. But in layers that correspond to the time of the Maya decline, the sediment changes. It becomes coarser, grittier, and interspersed with crystals of a white mineral called gypsum. Gypsum forms when lake water evaporates under hot, dry conditions, leaving its chemical components behind to crystallize. Its presence is a direct mineral signature of drought, a stark white line in the mud saying the water was disappearing. An even more precise thermometer and rain gauge comes from the tiny shells of aquatic creatures preserved in the sediment. The shells incorporate oxygen from the water as they grow, and the specific type, or isotope, of oxygen atoms they absorb changes with temperature and evaporation. By measuring the ratio of these oxygen isotopes in shells from different layers, researchers can reconstruct past rainfall and temperature with remarkable detail. What this evidence reveals is not a single bad season, but a pattern of profound climatic stress. Multiple studies now point to a series of intense, multi-decadal droughts that gripped the region precisely during the centuries of the classic Maya collapse. These were not mere dry spells. They were generations-long shifts where the rains became unreliable and the reservoirs and canals the Maya so carefully built began to empty. The silent archives in the lakebed show us a civilization that had pushed its agricultural system to a brilliant but precarious peak, only to have the climatic foundation it depended upon slowly pulled out from under it. The story shifts from a sudden mystery to a slow-motion strain, where the very ingenuity that built the empire may have made it more vulnerable to the changing sky. But a timeline built on mud and pollen alone has a weakness. It is relative. We can see the order of events, but pinning them to a precise year and connecting a drought in one valley to a city's final days in another requires a global clock. This is where a catastrophe becomes a gift for science, deep within those same Central American lake cores, in layers that date to the 6th century. Researchers find a thin, ghostly band of volcanic glass. This is the calling card of the Tierra Blanca Jovan eruption of the Ilopango volcano, an event so colossal it blanketed the region in a layer of ash meters thick. For the Maya living through it, it was a disaster of unimaginable scale, likely reshaping societies in its immediate aftermath. But for archaeologists and climatologists centuries later, that same ash layer is something else entirely, a perfect timestamp. In scientific terms, it is an isochron, a line of simultaneous time, because that unique chemical signature of Ilopango ash fell across the entire region within a matter of days or weeks. It creates an identical marker in every natural archive it touched. Find that ash in a lake core in Guatemala, and you have a fixed point. Find it in a sediment record 200 miles away in Honduras, and you have synchronized those two timelines to the same instant. This is the power of Tephra. It turns a continent of separate stories into a single, connected narrative. So when scientists see the gypsum crystals and the shifting oxygen isotopes that spell drought in a core, they can look just above or below that Ilopango ash line and ask, did this dry period come before the eruption or after? How many years of poor rainfall passed between the sky-falling ash and the last dated monument in a nearby city? The volcanic layer locks the environmental evidence from the silent witnesses into the same calendar as the king's own stone records. It allows us to say with new confidence that the prolonged droughts revealed in the mud were not a distant possibility. They were the lived reality for generations of Maya during their civilization's most vulnerable chapter. The ash from the sky becomes the key that synchronizes the story of the changing earth with the story of human history. The evidence from the pollen and the mud forms a powerful, three-part narrative of strain. First, the pollen map shows a landscape pushed to its productive limits. For centuries, the Maya successfully expanded their farmlands, clearing forests to plant more maize to feed a growing population. Yet this very success created a vulnerability. Deforestation can lead to soil erosion, washing away the fertile top layer that crops depend on, and some sediment studies suggest this process was underway. The society was operating at a high level of agricultural intensity, a system that required stability to function. Then came the second act, recorded by the gypsum crystals and oxygen isotopes, the prolonged droughts. A climate that had been reliable became unpredictable. The rains that filled the intricate canals and reservoirs grew scarce. This intersection is critical. A society already living close to the edge of its environmental capacity was then struck by a climatic shift that lasted for generations. The result, hinted at in the final layers of the silent record, was likely a cascade of hardships. Crops that depended on consistent water would have failed not just once but repeatedly. In a civilization where royal authority was partly derived from a king's perceived ability to communicate with the gods and ensure rain and plenty, such persistent failure struck at the heart of the social contract. We can envision, without needing graphic detail, how years of poor harvests would place immense strain on any community. Resources would become scarce. The central authority, unable to provide solutions, would see its legitimacy weaken. In this light, the abandonment of the great cities begins to look less like a single mysterious event and more like a slow unraveling. People may have gradually moved away from the stressed heartland, migrating towards areas with more reliable water sources, fracturing the political and economic unity that defined the classic period. The silent witnesses do not record a battle or a single decree, but they paint a compelling picture of a brilliant civilization meeting a combination of internal environmental pressure and external climatic change, a convergence that ultimately proved too much for its social structures to withstand. Yet the story told by the Pollen is not a simple one of cause and effect. The same environmental pressures that unfolded in the southern lowlands played out very differently elsewhere in the Maya world. While cities like Tikal and Kapon faded, other centers to the north, in places like Chichen Itza and the Puk Hills, not only endured but entered a period of remarkable new growth. The silent witnesses in their lakes tell a different tale. Sediment cores from the Yucatan Peninsula show a landscape that adapted. Here, the Pollen record reveals a continued, thriving human presence, but with a notable shift in strategy. Alongside the familiar maize, scientists find increased evidence of drought-resistant crops like cotton and agave, plants better suited to a drier climate. The northern Maya were not merely surviving, they were innovating, diversifying their agricultural portfolio in response to the changing conditions. This crucial detail complicates the narrative of a single, climate-driven collapse. It suggests that the environmental stress was a powerful catalyst, but not a universal sentence. The varying fates of different Maya regions point to something equally important: the role of human resilience. Political flexibility, economic networks, and social cohesion became the deciding factors. Some city-states, perhaps through better water management, more diversified trade, or more adaptable leadership, found ways to navigate the hardship. Others, whose systems were more rigid or whose environments were pushed past a tipping point, could not. The lesson from the Pollen is not that climate change doomed the Maya, but that it exposed the underlying strengths and weaknesses of their societies. It was a test, and different communities passed or failed based on a complex web of human choices, not just the whims of the weather. This moves us from a story of fate to a story of contingency, where the environment sets the stage but people write the script. While the Maya story is one of a civilization strained by its own success in a changing climate, another vanished society offers a starkly different setting for the same questions. Far to the north, on the frozen fringes of the Atlantic, the Norse settlements of Greenland present a haunting counterpoint. For nearly 5 centuries, a community of Scandinavian farmers clung to life in 2 remote outposts, raising livestock, building stone churches, and trading walrus ivory with Europe. Then, by the middle of the 15th century, they were gone. No chronicle records their final days. The only things left behind were the crumbling walls of their farms, silent under the Arctic sky. For historians, it became the ultimate cold case, a European society that simply evaporated from the map. The written record is sparse and silent, but the land itself holds a different kind of testimony. To understand what happened to the Greenland Norse, we must ask what their world was telling them and what they chose to hear. This mystery turns not on pollen from tropical lakes, but on 2 other silent witnesses: the ancient ice of the Greenland ice sheet and the discarded bones of the animals they relied upon. What story do these frozen archives tell about a society that chose to live at the very edge of the possible? The Greenland ice sheet holds a 500-year diary of the weather the Norse experienced. To read it, scientists drill deep, extracting slender cylinders of ancient ice like the famous Gisp-2 core. Each annual layer of snowfall, compressed over centuries, is a frozen snapshot of that year's atmosphere. Within this pristine archive, 2 chemical signatures are especially telling. The first is locked in the water molecules themselves. By measuring the ratio of different oxygen isotopes in the ice, researchers can reconstruct past temperatures with surprising precision. A higher proportion of the heavier oxygen isotope generally indicates a warmer climate, while a lower proportion points to colder years. The second clue is sea salt. Layers with high concentrations of sodium indicate stormier conditions over the North Atlantic, as fierce winds whipped more salt spray into the air to be carried inland and deposited on the ice. Together, these proxies paint a detailed picture of the climate the Norse settlers relied upon. The early layers, dating to their arrival around 980, tell a story of relative mildness. This period, often called the medieval warm period, is visible in the ice as a stretch of centuries with generally favorable oxygen isotope ratios. It was a window of opportunity, a time when the North Atlantic was less choked with sea ice, allowing ships to pass, and when growing seasons in Greenland, though always short, were perhaps a bit more reliable. This was the climate that invited settlement and made a distant pastoral life seem tenable. But the ice core record does not show a stable world. As the centuries passed, the chemical story within the ice begins to shift. The oxygen isotope ratios trend downward, signaling a gradual cooling. Concurrently, the sodium levels often spike, hinting at more frequent and violent storms raging across the ocean that connected the settlers to their homeland. This transition marks the onset of what historians term the Little Ice Age, a prolonged period of climatic cooling that reached its peak long after the Norse were gone, but whose early phases they would have endured. The ice tells us the environment that had welcomed them was slowly turning more hostile, bringing colder summers that stressed their pastures and longer, more extensive sea ice that could isolate them for years, severing the vital maritime lifeline to Iceland and Norway. The silent witness of the ice does not record a single catastrophic winter, but a relentless, generations-long trend. A slow tightening of the climatic vise around two fragile communities on the edge of the world. Yet the ice cores only tell half the story, revealing what the climate was doing to the Norse. To understand why they ultimately could not withstand it, we must look at what they were doing to the land. The answer lies not in the frozen heights, but in the quiet mud of lake bottoms near their abandoned farmsteads. When scientists extract sediment cores from these lakes and analyze the pollen trapped inside, they uncover a profound and telling puzzle. The pollen map paints a picture of a community clinging to an identity. Across centuries of occupation, the dominant pollen types are grasses, specifically the kinds cultivated for hay. This is the signature of a pastoral society, one focused on raising cattle, sheep, and goats, just as they had done back in Iceland and Norway. The landscape was being managed to support a European way of life, with meadows carefully maintained to produce winter fodder. What is strikingly absent from this pollen record is just as revealing. There is little to no evidence of a shift toward more cold-hardy, native plants or any significant adoption of the local flora that sustained the Inuit neighbors who thrived in the same environment. The Norse were not learning to farm the Greenlandic landscape on its own terms. They were relentlessly trying to recreate a Scandinavian farmstead upon it, season after season, even as the ice cores tell us those seasons were growing colder and shorter. This commitment extended beyond the fields and into the sea. The silent witness of archaeology adds another layer to this story. While the Norse did hunt caribou and seal, the sheer volume of animal bones found in their middens or garbage heaps tells a specific tale. The bones are overwhelmingly from their domesticated animals. The bones of wild seals and walrus are present, but largely from seasonal hunting excursions likely focused on the valuable ivory trade, not on securing a primary food supply. Most telling of all is the near-complete absence of fish bones. For a community living on fjords teeming with marine life, this is an astounding omission. Fishing was a cornerstone of Inuit survival and a skill the Norse possessed from their homelands, yet in Greenland, they seemingly turned away from this abundant, reliable protein source. The pollen from the lakes and the bones from the ruins converge on a single, powerful conclusion. The Norse in Greenland were not just settlers, they were cultural traditionalists. Faced with a changing and challenging environment, their response was one of deep conservation. doubling down on the familiar practices that defined them as Europeans, as Christians, as farmers. They maintained their diet, their architecture, their social structure, and their economic links to a distant homeland, even as those links grew more tenuous with every stormy season recorded in the ice. In their silence, the pollen grains and the animal remains speak volumes about the power of cultural identity and the potential peril of adhering to it when the world you inhabit demands adaptation. The very ice that recorded the slow cooling of the Norse world also captured moments of sudden, violent change. Within the meticulously layered ice cores from Greenland, scientists find delicate bands of gray, fine particles that are not snow. These are layers of volcanic ash or tephra carried by the wind from eruptions in Iceland, hundreds of miles across the sea. Each of these ash layers is a unique chemical fingerprint, a perfect timestamp frozen in the glacier. When researchers match an ash band in the ice to a historically documented Icelandic eruption, like the massive event at Eldgjá in the 10th century, they can assign an exact year or even season to that specific layer in the core. This turns the ice into a dated calendar, allowing us to line up the climatic data with human events with incredible precision. But these ash layers are more than just inert bookmarks. Following some of the largest eruptions, the chemical analysis of the ice tells a secondary story. The layers immediately after the ash often show a sharp spike in sulfuric acid. This is the atmospheric signature of the volcano having ejected vast quantities of sulfur dioxide gas high into the stratosphere, where it forms aerosols that reflect sunlight back into space. The result, recorded in tree rings and historical accounts from Europe to Asia, is a period of global cooling, often lasting a year or more. For the Norse in Greenland, an Icelandic eruption meant more than just a hazy sky. It could trigger a year without a summer. A single ash-identified eruption in the ice core record could be followed by a sudden, acute dip in temperature. A summer so cold and short that the already stressed hay fields would fail completely. This added a layer of acute, catastrophic stress on top of the slow, grinding pressure of the long-term climatic cooling. One bad harvest could deplete crucial fodder reserves, leading to the loss of livestock, the very foundation of their wealth and survival. The ice, therefore, tells a dual tale. It charts the inevitable, gradual trend of the Little Ice Age, and it marks the precise moments when volcanic fury delivered a sharp, punishing blow to a society already living on the edge. The story that emerges from the ice and the pollen is one of a slow, quiet convergence. On one side, the climate was tightening its grip, bringing colder summers and more treacherous seas. On the other, a community held fast to the only life it knew. The archaeological record adds a final, poignant layer to this picture, a steady decline in imported goods from Europe, things like iron tools, glass beads, and quality timber. As the sea ice lingered longer and the voyages became more perilous, the lifeline to their cultural homeland grew thin and finally snapped. They were not just geographically remote, they were becoming culturally and economically marooned. The evidence paints a portrait of a society caught in a trap of its own making, facing a deteriorating world with a strategy that had not changed since the day their ancestors landed. The pollen shows a steadfast commitment to European pasture grasses. The bone middens show a reliance on livestock that those very grasses could no longer reliably support in the lengthening cold. The silent witnesses point not to a sudden catastrophe but to a protracted generational strain. In such an isolated and resource-strapped environment, this inflexibility would have had profound consequences. We can understand from a historical distance how years of poor harvests would place immense stress on a community. A diet lacking in diversity, coupled with the relentless physical demands of their lifestyle, could lead to widespread health challenges. Researchers studying the few remains from the latest period note signs of nutritional stress and a population that was shrinking, not from a single event, but from the accumulated hardship of a way of life that was no longer sustainable in that place at that time. The end, when it came, was likely not dramatic. It was the quiet culmination of a long process, a final, difficult decision made by the last families that there was simply no future left on those farms. They packed what they could and sailed away, or perhaps stayed until there was no one left to leave. The walls they left behind stand as a monument to human endurance, but also to the profound lesson written in the ice and the dirt, that survival often depends less on sheer will than on the capacity to change. The story of the Norse is one of a society shrinking in isolation, its choices written in the local pollen and ice. But what about an empire so vast its influence was not contained by any one landscape? The Roman Empire was a civilization of a different magnitude, a sprawling economic machine that consumed resources from Scotland to the Sahara. Its power was measured in legions, laws, and monuments, but its true scale may be recorded somewhere far more remote. High on the Greenland ice sheet, thousands of miles from the Forum, a silent and astonishing ledger was being kept. Deep within the frozen annual layers, scientists have found a chemical whisper of Roman industry, a global signature of its economic pulse. This raises a profound question for our investigation. How can the purity of Arctic ice reveal the industrial heartbeat of an ancient Mediterranean empire? Buried within the pristine layers of Greenland's ice is a ghost of Roman prosperity. When scientists analyze those ancient, trapped air bubbles, they find a startling chemical signature: trace amounts of lead. This is not a constant background level. It appears in dramatic spikes and troughs, forming a precise graph of industrial activity over centuries. The most pronounced of these spikes align perfectly with the height of the Roman Empire, from around the 1st century before the Common Era through the 2nd century of the Common Era. This lead traveled over 3,000 miles from the heart of the Mediterranean to the remote Arctic, carried on the global winds, a permanent atmospheric stain from one of history's greatest economic engines. But why lead? The answer lies in the foundation of Roman wealth: silver coinage. The primary source of Roman silver was a mining process called cupellation. Miners would first extract silver-rich lead ore, often from massive mines like those at Rio Tinto in Spain. This ore was then smelted at high temperatures. Because lead has a lower boiling point than silver, the lead would vaporize into the air as a toxic fume, leaving behind the purified silver. For every pound of silver coin minted to pay soldiers, fund public works, and grease the wheels of trade, pounds of lead were released into the atmosphere as an invisible industrial byproduct. Those lead particles, lifted by the heat of countless furnaces, were caught by the wind, traveling north across Europe and eventually settling with the snow on Greenland. Each snowfall locked in a tiny sample of the Roman economy. By measuring the concentration of lead in each annual ice layer, scientists can essentially chart the empire's industrial output year by year. The peaks in the graph correspond to periods of intense political stability and economic expansion, like the Pax Romana under emperors like Augustus and Trajan. During these eras of peace and infrastructure projects, the demand for silver coinage was enormous, and the mines operated at a furious pace. The ice records this boom with startling clarity. Conversely, when the graph dips, it often mirrors times of crisis, civil war, or pandemic, when mining and smelting activity would have slowed or halted. The silent ice, therefore, becomes a remote financial ledger, an objective record of imperial good times and bad, written not by a historian with an agenda, but by the very pollution of progress. It tells us that the reach of Rome was not just political or military, it was chemical, literally changing the composition of the global atmosphere. The graph written in Greenland's ice is astonishingly precise. It begins as a faint whisper around the 2nd century before the Common Era, as the Roman Republic consolidated its hold on the Mediterranean. Then, as Augustus secures power and ushers in the Pax Romana, the line on the graph shoots upward. This is the empire's economic heartbeat at its strongest, a 200-year period where the lead concentration in the ice remains consistently high. The furnaces in Spain and elsewhere burned day and night, minting the silver denarii that paid the legions guarding the frontiers, funded the aqueducts bringing water to cities, and facilitated trade from Britain to Egypt. The ice core data quantifies this golden age not in poetic terms, but in parts per trillion of atmospheric lead, a direct measurement of industrial confidence and imperial reach. But this steady pulse does not last. In the middle of the 3rd century of the Common Era, the graph takes a sudden, precipitous dive. This corresponds exactly to the period historians call the crisis of the 3rd century, a 50-year span of relentless turmoil. The empire fractured, with rival generals constantly fighting civil wars, foreign invasions piercing the frontiers, and a devastating pandemic sweeping through the population. In such chaos, the complex state-run mining and smelting operations could not continue. The mines likely fell idle, were seized by local warlords, or simply became too dangerous to operate as infrastructure and security broke down. The Greenland ice records this collapse in stark terms, the lead pollution plummeting to levels not seen since before the empire's rise. The silent witness suggests the mighty Roman economic engine had, for a time, nearly ground to a halt. There is a brief, telling recovery later in that same century. The line on the graph climbs again, though it never quite reaches its former peak. This mirrors the historical record of emperors like Aurelian and Diocletian, who fought desperately to reunite the empire and restore order. Their reforms, including a major overhaul of the currency system, required a renewed burst of silver production, and the ice captures this last gasp of centralized imperial effort. It is a flicker of the old pulse, a sign of the empire struggling back to its feet. The final act is one of quiet fading. After the 4th century, the lead signal in the Greenland ice begins a long, irreversible decline. It fluctuates, but the trend is steadily downward. By the 5th century, following the political dissolution of the Western Roman Empire, the lead pollution falls to near zero levels, a baseline not seen for over 500 years. The great smelting centers were abandoned, the trade networks that distributed the coins fractured, and the economic unity that had defined the Mediterranean world dissolved. The ice did not record the sack of Rome or the deposition of the last emperor, but it recorded the profound and lasting economic consequence, the silencing of an industrial hum that had once been audible from one end of the earth to the other. This provides something written chronicles often lack, a quantitative year-by-year proxy for the intensity of the Roman monetary economy. We are not reading a historian's opinion on the strength of an emperor's reign. We are reading the empire's own financial vitals, taken from an atmospheric sample and showing, with cold, hard data, the exact moments its heart raced, faltered, and finally stopped beating. The lead in the ice recorded the empire's economic pulse, but another chemical signature captured a moment when the sky itself seemed to turn against the world. In the layered ice cores from both Greenland and Antarctica, scientists have identified a staggering spike of sulfuric acid dating precisely to the year 536 of the Common Era. This is the unmistakable fingerprint of a colossal volcanic eruption, one so powerful it ejected millions of tons of sulfur-rich gas high into the stratosphere, where it formed a veil of aerosols that dimmed the sun across the entire planet. The historical records that survive from this period are chilling in their unanimity. Byzantine historian Procopius wrote of a mysterious, persistent dust veil that blotted out the sun's light for over a year, bringing a cold so deep that summer never truly arrived. Accounts from Europe to China describe the sun shining with the dull glow of the moon, frosts ruining crops in August, and widespread famine. This was the original year without summer, a global climatic shock triggered by a natural event of terrifying scale. The exact volcano responsible remains one of history's great geological mysteries, with candidates suggested from Alaska to the tropics, but the evidence in the ice is unequivocal. For over 18 months, the world grew dark and cold. This event did not cause the fall of the Western Roman Empire, which had politically dissolved decades earlier. Instead, it struck a post-Roman world already grappling with immense fragility. The intricate trade networks that once distributed grain from North Africa to Britain were fractured. The centralized authority that might have coordinated a response to famine was gone, replaced by smaller, weaker kingdoms. The Volcanic Winter of 536 arrived as a catastrophic multiplier of existing hardship. Crops failed repeatedly across Europe and Asia. The resulting famine would have weakened populations, making them more susceptible to illness. It is within this context of climatic stress and social disruption that historians note the first great wave of the Justinianic plague emerged just a few years later, spreading with devastating effect through a world already under profound strain. The sulfuric acid line in the ice, therefore, is more than just a record of a natural disaster. It is a pivotal timestamp that helps explain why the centuries following Rome's political collapse were so acutely difficult. The societies trying to rebuild in the empire's shadow were not just navigating political change, they were struggling to survive under a literally darkened sky, fighting for sustenance in a world that had grown suddenly and inexplicably colder. This silent witness in the polar ice transforms our understanding of the so-called Dark Ages, framing it not merely as a period of cultural forgetting, but as an era of profound environmental challenge that tested human resilience to its limit. While Roman lead faded from the air, a quieter but equally profound transformation was taking root across the European landscape itself. The pollen record from lakes and bogs tells a story not of industry, but of its sudden absence and of nature's patient reclamation. As the complex systems of the Roman world faltered, the meticulously managed agricultural countryside began to change. Fields that had fed legions and cities for centuries were no longer being plowed, sown, or harvested. The land was left fallow, and the silent witness of pollen reveals what happened next with stunning clarity. In sediment cores from Britain to Italy, researchers see a dramatic and rapid shift in the botanical record. The pollen of cereal crops like wheat and barley, along with the weeds of cultivated fields, begins to plummet. In their place, a new signature emerges, the pollen of fast-growing, sun-loving pioneer trees. Birch and pine, species that quickly colonize open ground, show a massive spike. This is the first stage of the forest's return, a green wave washing over abandoned Roman villas, empty farmsteads, and untended roads. For a generation or two, these hardy trees dominated the landscape, stabilizing the soil and creating new conditions. Then, as the pollen record continues, a second, slower wave follows. The birch and pine pollen gradually declines, replaced by the spores of mature forest giants, oak, beech, and elm. This succession, from field to pioneer scrub to deep, established woodland, is a textbook ecological process. But in this context, it is not just a natural event, it is a direct physical measure of human history. That dense, climax forest could only establish itself if the land remained undisturbed for a very long time, likely a century or more. The pollen becomes an indirect census, revealing a countryside where the human footprint had lightened dramatically. This was not a localized event, it was a continental-scale phenomenon, visible from the highlands of Scotland to the plains of France. The sheer geographic spread of this reforestation signal provides undeniable physical evidence for what historians had long suspected: widespread rural depopulation and a profound contraction of organized agriculture following the empire's dissolution and the crises of the 6th century. The forest did not creep back, it surged, and in its pollen we can trace the slow, deep breath of a land recovering from centuries of intensive human use. These separate stories from the Maya, the Norse, and the Romans begin to converge into a single, powerful lesson. When we view them through the lens of pollen, ash, and ice, cross-cultural patterns emerge from the silent data. First, we see a recurring theme of expansion to environmental limits, written clearly in the pollen record. The Maya transformed their rainforest into a vast maize field. The Norse maintained European pastures on a Greenlandic coastline. In each case, a successful society pushed its agricultural system to a peak of productivity, creating a landscape finely tuned to a specific way of life. This success, however, built in a profound vulnerability, a dependence on a stable climate to support that intensive, specialized system. The second pattern is the indelible mark of economic activity, captured in remote ice. The Roman-led pollution is the most dramatic example, but the principle is universal. Every large-scale civilization, through mining, smelting, deforestation, or large-scale farming, alters the chemical and physical makeup of its environment. These changes can travel on the wind, leaving a signature far from their source. Our modern world is no different. We are simply writing our signature in different chemicals, like carbon dioxide and novel pollutants, that future researchers will one day find in glacial ice yet to form. The third and perhaps most crucial pattern is the role of the climate itself. In story after story, the silent archives show that periods of great societal stress or transformation are frequently accompanied by climatic stresses. For the Maya, it was prolonged drought. For the Norse, it was the creeping cold of the Little Ice Age. For the post-Roman world, it was the volcanic winter of 536. The ash layers and the isotopic records in the ice act as a global check, reminding us that human history does not unfold on a static stage. The stage itself is constantly shifting, sometimes gradually, sometimes with sudden, catastrophic lurches. Yet here lies the most important insight of all. The climatic stressor is rarely the sole cause of collapse. It is the catalyst, the test, the ultimate outcome. Whether a society adapts, migrates, or fades is determined by its resilience. The Maya of the northern Yucatan diversified their crops and thrived, while their southern cousins did not. The Norse in Greenland clung to tradition in the face of a changing world, while the Inuit, with a flexible, technology-rich culture built for the Arctic, not only survived but expanded into the same spaces. Resilience is found in the capacity to innovate, to adopt new foods, to form new social bonds, and to let go of practices that no longer serve survival. The silent witnesses do not judge, they simply record the results of these human choices against the backdrop of an evolving planet. They reveal that the fate of civilizations is not written in the stars, but in the intricate, often fragile, relationship between a society's choices and the world it inhabits. But this powerful story has its own built-in caution. The silent witnesses speak, but their language is not always easy to translate. The first challenge is the calendar itself. While a volcanic ash layer can provide a perfect, instant timestamp, most sediment layers are not so neatly marked. Dating a layer of mud using radiocarbon methods on a single leaf or piece of charcoal gives a range often spanning several decades. This means the pollen shift we see in a core might tell us a forest regrew sometime in the 6th century, but it cannot tell us if that regrowth began before or after a specific political event like a king's death or an invasion. The timeline is sometimes fuzzy, making it difficult to say with absolute precision whether an environmental change came first and caused a human response, or whether a human collapse came first and allowed the environment to change. Scientists must work carefully to align these proxy records with archaeological evidence, knowing they are often working with probabilities rather than certainties. Another persistent puzzle is separating the human hand from nature's own variability. A decline in tree pollen in a sediment core could signal deforestation by farmers clearing land. But it could also be the result of a natural wildfire, a disease that swept through a forest, or a shift in regional rainfall patterns that simply made the conditions less favorable for those trees. The evidence is often ambiguous. Researchers look for corroborating clues, like a simultaneous increase in the pollen of crops or weeds that thrive in open, disturbed ground, which would point more strongly toward human activity. They also compare multiple cores from across a region, because human impact tends to create a more localized, patchy pattern, while a widespread climate event would leave a more uniform signature. It is a meticulous process of elimination, building a case by ruling out other possibilities. This leads directly to the most important debate in the field, the classic problem of correlation versus causation. Finding a layer of drought evidence in a lake core that dates to the same century a city was abandoned is a compelling correlation, but does it prove the drought caused the collapse? Not necessarily. It could be that political instability and warfare led to the abandonment, which then changed land use and affected the local water cycle, creating the drought signal in the lake. Or both the societal stress and the environmental stress could have been caused by a third factor, like a series of volcanic eruptions disrupting climate patterns. The silent archives show us that things happened at the same time, but they do not, on their own, tell us the order of events or the chain of cause and effect. They provide the environmental context, the backdrop against which the human drama played out. This is why the true power of this science lies in integration. Pollen, ash, and ice are not meant to replace the work of archaeologists digging through ruins or historians deciphering ancient texts. They are meant to converse with them. A historian's record of a famine in a certain year gains profound new meaning when an ice core reveals a global volcanic winter at that exact moment. An archaeologist's finding of smaller, less nutritious livestock bones in a settlement's final layers is powerfully explained by a pollen record showing the degradation of local pastures. Each line of evidence corrects the biases of the others. The monuments boast of eternal glory, while the soil whispers of exhausted fields. The chronicles record the deeds of kings, while the ice graphs the economic health of the Commonwealth. By weaving these threads together, we move closer to a holistic history, one that respects the complexity of the past. It reminds us that civilizations are not just ideas or armies. They are physical entities built from soil, water, and air, and their stories are written in those very elements, waiting for us to learn how to read. This conversation between soil and sky is not confined to the ancient past. The very same scientific techniques that read the stories of the Maya and the Romans are now being used to define a new geological epoch, our own, the Anthropocene. Researchers are drilling into modern sediments, analyzing ice cores from glaciers that are themselves vanishing, and collecting pollen from urban parks. What they are finding is a planetary signature unlike anything in the record. The lead from Roman smelters has been replaced by a cocktail of novel chemicals, plastics, and radioactive isotopes from nuclear tests. The localized deforestation seen in medieval pollen cores is now a global pattern, visible from satellites. The rate of change recorded in these modern archives is staggering, compressing transformations that took ancient civilizations centuries into mere decades. We are writing our history into the Earth's strata at an unprecedented pace, and the silent witnesses are recording every line. The past, therefore, offers us more than just fascinating stories. It provides a framework for understanding our present moment. It shows us that societies, no matter how grand, exist in a dynamic relationship with their environment. The cases we have explored reveal a common theme. Vulnerability often arose when a culture became too specialized, too rigid, or too disconnected from the ecological foundations that supported it. They faced challenges from drought to cooling climates that tested their capacity for resilience. Our global civilization now faces its own suite of environmental pressures, from shifting climate patterns to resource constraints. The lesson from history is not that collapse is inevitable, but that the outcome hinges critically on the choices we make. The past suggests that longevity is found in flexibility, in the ability to diversify, innovate, and adapt our practices to the realities of a changing world. It reminds us that the most enduring legacy a society can leave might not be its monuments, but a stable and healthy planet whose silent records tell a story of balance rather than strain. The clues we leave in the pollen, the ash, and the ice are still being written. What will they say about us? The silent archives are far from a closed book. As technology advances, the very definition of a clue is expanding, allowing scientists to read these ancient records with a resolution once thought impossible. One of the most exciting frontiers is the analysis of ancient DNA preserved in sediments, known as cedar-DNA. Imagine being able to detect not just the pollen of a grass, but the specific genetic signature of the domesticated maize variety a Mayan farmer planted, or the gut microbiome of the animals that grazed a Norse field. This is the promise of cedar-DNA. By extracting and sequencing the minuscule fragments of genetic material trapped in lakebeds and soils, researchers can reconstruct entire ecosystems with stunning detail, identifying plants, animals, bacteria, and even humans from the microscopic debris they left behind. It is like upgrading from a blurry black and white photograph of a landscape to a high-definition, full-color genomic map. Concurrently, ice core science is achieving its own revolution in precision. New drilling techniques and analytical instruments can now resolve ice layers down to a seasonal scale, distinguishing summer snow from winter snow in cores that are hundreds of thousands of years old. This allows scientists to pinpoint climatic events, like a particularly harsh winter or a volcanic eruption, to a specific year and even a specific season, syncing human history with environmental history on an almost monthly basis. These tools are now being turned toward history's great unresolved puzzles. The sudden, sweeping collapse of Eastern Mediterranean civilizations around 1200 before the Common Era, known as the Late Bronze Age collapse, has long been attributed to a mysterious confluence of invasions, earthquakes, and social unrest. But what was the environment doing? New sediment cores from the Aegean and Anatolia are being analyzed for pollen, ash, and now cedar-DNA, searching for evidence of concurrent drought, agricultural failure, or disease that could have pushed a network of interconnected kingdoms past a tipping point. Similarly, the gradual abandonment of Ankara, the magnificent capital of the Khmer Empire, is another prime target. While shifts in monsoon patterns are suspected, researchers are now using incredibly detailed analyses of sediment layers from the city's vast reservoir system to reconstruct annual rainfall patterns, looking for proof of the prolonged megadroughts that may have crippled its intricate water management network. Each core drilled, each genetic sequence decoded, is a new line in a global conversation between the past and the present. These mysteries persist not because the clues are absent, but because we are only now developing the language to ask them the right questions. These silent witnesses have rewritten our understanding of history itself. Pollen, ash, and ice are far more than geological curiosities. They are primary sources, as vital as any manuscript or monument. They tell us that the stories of the Maya, the Norse, and Rome were not tales of sudden, catastrophic endings. They were slow-motion processes unfolding over generations, made visible only through the patient testimony of the earth. Each collapse was a complex symphony of environmental stress, economic contraction, and societal choice, recorded with unwavering honesty in lakebeds, ice sheets, and layers of volcanic dust. The Maya did not vanish in a day. They grappled with centuries of agricultural strain and climatic shift. The Greenland Norse did not simply disappear. They faced a slowly tightening world while holding fast to an identity that could no longer sustain them. Rome's fall was not a single event, but a long economic fade, its pulse slowing until the final silence, all graphed in the remote Arctic ice. This science grants us a profound new sense of hearing. It allows us to listen to the past as whispered by the landscape itself, to understand civilizations not just as political entities, but as living, breathing parts of their environment. As we face our own era of global change, these archives from vanished worlds offer a quiet, powerful reflection. They ask us to consider what story our own civilization is now writing into the soil, the air, and the ice, and what whispers future generations might one day hear about the choices we made.